Thank you.
Sorry, I'm just getting the slides up now. It's taking a bit of time.
Oh.
Okay.
Okay.
All right, so I'm just going to share this screen, okay? So I had a few questions, and there seems to be a little bit of confusion. So let me get my laser pointer up. So essentially, some people are going through the tutorial, that other chute, with the sandstone chute. So when you're doing that, you're sort of up to this stage here, this last stage here. So there's several sort of phases of your experiment. So your first would actually be your sample creation, in which you would use the DCM program to, firstly, you want to look at your materials and see if they're compatible. So you might, let's just sort of go from the very start. You've got some, say, coatings that you're interested in scanning and, say, measuring the porosity, or you might want to measure the two different phases and image them. So your first phase would literally be to look and see if what you're planning to scan is actually going to be worth scanning. So remember, this is where we add our compositions to DCM, and then we look at them over the different energy ranges. So that's sort of your first phase. And after that, that's when you can say, okay, yes or no. You make it to the stage where, you're looking at it and you go, well, I actually can't do that. I have to rethink my experiment. So first phase is actually picking your samples and then using the composition panel in the DCM software to figure out your the size. So remember, this is, you use the 30 and 70% range, and that's all in DCM. I showed you how to do that, but you can actually just use DCM to do that. And that's when you've got your samples. Then you'll go off and you'll scan them somewhere. This may be at a synchrotron, it may be somewhere else. And then the outcome of that is 2 here. So this is your projection images, or one of your projection images. The next step is just a simple one. So you're going to be just trimming it. And basically this is just reducing the time. When you're trimming it, give it a little bit of space. You don't want to try and trim really, really, really close to your sample. Give it a little bit of space. And then you're actually going to be processing it in either extract or another program. So in this here, this is where you've got a whole bunch of projection images. You've got your dark field images, you've got your bright field images, right? When you're processing them, the outcome is a bunch of 2D reconstructed images. This thing you see right here, this has already been corrected. So your dark field, your bright field, it's this image here you see has been processed. It's had, you can see there's a little bit of ring artifact in here, but to the best of its ability, it's removed the ring artifacts. So in this process here, this is where you're doing all of the sort of the CT reconstruction and processing those projection images. When you get to here, so this is where you're up to in your sandstone tutorial. So essentially, all of this has been done. So the images that you're importing into your channels, your energy channels, what is 70 or 90 kilo electron volts, whatever it is, they're these images that have already been corrected. They're CT reconstructed 2D images, and you're importing them in. And then you're running the computations. So those images that you're importing, they're already processed. So I had a question sort of saying, where are the dark and bright field images? Why aren't we importing them in this stage into DCM? Because all of those corrections have already been done in the CT reconstruction stage. So it's very phasey, and you should probably try and break it up into phases and think of it sort of that way. That's why I sort of have these images set up. But yeah, so when you're doing the sandstone, you're really at this final stage. So really, there are a fair few stages beforehand that you need to get your head around.
Okay, and maybe I'll just add to that. For training is there are 2 purposes. One is if your projection image has a bad area, and that may cause trouble when you do the reconstruction. So you need to get rid of that. And another added benefit to trimming is yes, reduce, make the images smaller so you save a bit of storage space. But mainly is if you like that image, you get the black top and bottom, and that part is bad. If you just use that, you may cause a trouble, reconstruction process.
Yeah, actually, I do have something to add to that as well. Also, Sam.
And a lot of the time, most of the time, actually, you don't need to do any trimming. It's only in some cases, and for certain setup, you may have part of the projection image no good, and you need to get rid of it.
Yeah. So what I was going to say is when you're importing those images, you know, it'll be S200 or S300 to whatever. It's generally good to sort of start around 150 or 200 and not to go too far down. So right in the middle is when you're going to get your sort of best area to look at. So I always go around 300 to 600, or depends on how big your sample is, but I always found the middle bit to be the best to look at.
Okay, that's all related to the particular setup.
True. Yeah.
Right. Okay.
But we can set the boundaries by ourselves in the DCM as well. Yeah.
Sorry.
Or is it a different one? We set the boundaries as well in the DCM. Boundaries.
I missed it. Sorry.
Like we can set the boundaries in the DCM as well.
Boundary is later analysis.
Yes.
All right. So
yeah.
there's a boundary means that you just, if you want to focus your sample area.
Okay.
And you can define a various your sample and analyze.
Okay. By doing that, we cannot trim the sample. If we are
the boundary and a trimming is a totally different thing.
Okay.
Trimming the images. If you find there is a bad region of the image,
okay,
and you don't want to use it because very often in reconstruction you may just blow up with error message and say it's a bad image, so you need to get rid of it. Boundary is a defined shape of the sample. They are totally different things.
Okay, yes.
But what you can do is once you have your sample grid and you've done your computations, you can reset your sample grid size, and pick a certain area. It can be a little bit trial and error, sort of tricky to get the right bits, but that is one way of looking at a portion, and another way is to apply boundaries. So it depends on your scans, I guess. So with my recent work, there's several different ways of creating the boundaries, and some strategies work and others won't on differing samples. So it's a bit that part's up to you, and you may need to be a bit creative with coming up.
A lot of the cases you don't need to worry about the boundary. A lot of cases you just look at the inside the sample, and you don't need to worry about the boundary. So, like the sandstone, the case, there's no boundary. That's the inside the sample. No sample boundary. Okay. So has anyone actually tried to work in your own case?
One more thing I'm a little bit confused about. Like I know you explained it a lot last time, the molar mass of the molar mass. Like if we are taking the sample like titanium is 90% and the ceramic powder, we are mixing it with the ceramic powder is 10%.
Yeah.
So how we will doing the composition of the in DCM? Like we're going to write an empirical formula for that.
Okay. First of all, do you understand what is a molar percentage?
Yeah, I also calculated the molar percentage of titanium diboride as well.
Yeah.
Yeah.
Because
Atomic weight and number
the
of the atoms in the
titanium and the titanium, all the ceramic particles are mixed.
yes,
So that's one material.
yes,
So you just get a molar formula for the whole thing.
yeah.
Maybe I think Emma is familiar with. She should be familiar. Just if for argument's sake we have Ti6 for 90% weight by weight, and 10% is just for argument's sake, say titanium carbide. You treat the whole thing as one material and work out a molar formula. Does anyone want to explain how to do that? Maybe I'll give Emma a challenge.
I haven't done molar stuff in a good 10 years, so I kind of understand the concept of it, but I haven't actually practiced it for
Sorry.
quite a while. So I'm a
Right.
little bit rusty on it.
Okay. Whoever is familiar, Shima, are you familiar? You're familiar with?
Like I try to do that, but I know it's not correct. The last part. Like I do the molar mass of titanium diboride. I tried with the titanium diboride and titanium CPTI.
The TIB2 is already in molar. So the TIB2 is the actual molecular formula.
Yeah.
So it's an RB2, TIB2, that is the molecular formula. So
Yeah.
that's already in molecular. So you don't need to do anything with that one there.
So
this TIB2 is the molecular formula. So I don't have something like this. Can you stop sharing this for a sec? Let me share something. Can you? Yep. So, oh, sorry, I did that wrong. Okay. So, what I want you to look at is down here. Okay, see this here?
Yes.
TI 86.2, AL 10.2, V 3.6. That's the molecular formula of titanium 64.
Yeah.
So titanium 64 is 90%, 90 weight percent titanium, 6 weight percent aluminium, 4 weight percent vanadium.
Yes.
Okay, so you can't just put in, TI 0.9.
Yeah.
That's not going to be the right formula. You need to convert it to this sort of formula. So this is, and you can see that the way I've done it, I could divide it by 3, but the way I've done it here, 3.6, but the way I've done it here, it all adds up. So you can see 86.2 plus 10.2 plus 3.6, that's 100%. So it's a good way to do, to present it like this as well. So you can, that's just I guess a sanity check for yourself.
Yeah.
But the way you would do this is you would have 90 grams of, so you would say, the whole thing is 100 grams, say.
Yes.
So 90 grams of this would be titanium, 6 grams would be aluminium, and 4 grams would be vanadium. You divide those numbers via the molecular weight, and then you add those numbers up, and then that's your final amount. And then you go and divide those amounts that you had by that final amount, and that will get you the relative, out of 100%. I don't have it actually worked out, but it's fairly straightforward. So for this one, that's a good, yeah.
We'll get Senna to present it to see how you did it.
Okay. Actually, in my time, because we are going to use the CPTI, it's just the titanium in our case, because you're showing the titanium 64.
Yeah, that's the same principle. Can you bring it up and see how you did it, and so just get it, need everyone to understand.
Okay. I did for I checked the molar mass of titanium diboride.
Yeah.
So for titanium and for this, okay, it's a molecular formula already, but it gives me for when I calculate it, I I I suppose like that this titanium is 90 gram and titanium diboride we are going to take 10% and we are going to mix it up. So I think I should make a formula for that, the empirical formula out of
Yeah.
that.
Yeah.
And the molecule the atomic weight of titanium is 47.87. So I divided 90% with the
Ah,
47.87.
so the only mistake
Yeah.
you made is you have to add 1.88 and 0.143 together. Then you
Okay.
divide 1.8. You divide 1.88 divided by that whole amount, and the same on the other one. So that's
Okay.
the only,
Yeah.
that's the only
Yeah.
thing
Yeah.
you've
That's
done.
yeah.
Oh,
This the first one is all right. Okay.
okay.
For
This
TRP2,
yeah.
yeah.
So
I just need
1.88.
divide. I just need to add 1.88 as well. Yeah.
Yeah,
It is yes.
yeah,
Okay.
yeah,
Okay. Thank you.
Okay. So
yeah. That'll get you the fractions. Yep.
Yeah. Okay.
now the okay.
Hi. So in the third line for our sample, data 90% and data B2 10%, is that the percent of weight?
Sorry.
So when you say for our sample, data 90% and data
Yes.
DB2 10%,
Titan.
is that the percent of weight? Right. For example, I
Yes.
have
Yeah.
100 gram, so
Yeah.
90 gram will be the pure titan, right? And then 10 gram will be the DIB2. Right?
Yes.
Okay. The all right. You need all right. First of all, the where you get that 69,489
Which one?
for
The
the
mass one?
for the third line. What is that? 69.
This one 69.
No. You're
This
not
one.
fully in line.
Oh yeah.
16, yeah.
Yeah. I have
69,489.
yeah. I have calculated if TiB2 weight. It's like 47, the atomic weight of titanium and the two molecules of boron for that, and then multiply two item with the atomic weight of this, and then I got the weight
Okay,
for
yeah.
titanium diboride.
Okay. Yeah, so I think that
Uh,
69.489 is a
Weight of titanium diboride.
yeah, yeah.
okay.
Yeah.
So the oh, you add this two together, get that number.
Yes, because the titanium diboride, I just two multiply 2 by 10 the atomic weight of boron, and
Uh,
then
It's
add
correct.
weight is
It's correct.
incorrect. It
No,
makes
it's correct.
sense because you have 90% of titanium,
yeah, and then
all right, and you have 10% of TiB2,
yes, it's
right?
here, it's from here.
All right, their total density will be lower than titanium.
Okay.
Do you understand?
Yes.
When you mix a higher density and with a lower density material, your total density will be lower. So
Okay.
in this way, you work out to be a higher value. You cannot be right.
Okay. Yes.
Do you understand?
Yes.
Okay. So the first, you need to work out what is the density of the mix.
Yes.
That's a rule of mixtures. You know how to do the rule of
Okay.
mixtures. Yeah.
So all this, the calculation is not not correct. First, you need to work out what is the total density.
Okay.
This should be a simple exercise. Can
Yes.
anyone try
Yes.
to explain? Um, do you understand what I mean?
Yes.
Okay. Can anyone else, like Emma, do you want to explain? What would be the the total density for when this two is mixed.
So the total density would just be wool mixtures. So 90% of it would be 40. You do 90% times by 47.86 plus 10%
No,
times by.
you need the actual density. So this is the as it is
Atomic
right
weight,
now.
sorry.
This is the molecular. So there's no density
so-
here. You need to get the
You need
densities
the
up in your
density.
table as well.
There's no
So-
density here.
So CP ties, I think 4.51, I think, and then I don't know
Yeah.
what type boy is, but presumably it'd be quite a lot lower. So whatever the density of type boy is, so I'll just have a look at that up.
Yep.
So well, actually titanium diborate is 4.52.
Yeah.
So it's, and CP ties 4.51. So it'd
Yep.
be essentially 4.5 something. But so you just do 90.9 times by 4.51 plus
Yep.
0.1 times 4.52, whatever
Yep.
that comes out to be.
Yep. Because this two just happened to be density very close. But that's the right way to do. So the first of all, you get the density incorrect.
Yeah.
No density quoted. Then you work out what is the total amount of mass for titanium.
Total mass?
Yeah. Oh, the mass percentage.
Okay.
So the answer is what you get is not correct.
Okay.
So the first of all, you need to get what is the total density and what is the formula, and use that to
get the mass
estimate the
percent.
sample. Okay.
Yeah.
Have you done any further than that, more than this?
Yeah. I try to run the file, check the DCM and the CIPS transform files, but let me check.
Okay.
I don't know. I run the computation, but I don't know why I didn't get anything.
Okay.
I take
I
the
think
dot.
that Simon had the same problem last time.
Yeah, I think
Yeah.
because that time actually have to select the scale because yeah, I
Scale?
think that yeah, well, when you import the data,
Yes.
yeah, maybe you try to import it again.
Yeah.
No, yeah, that one, yeah,
Yes.
import data, yeah.
Yes.
Yeah, you have to stick the rescale data by TV4. Yeah, no, so the first one, so the first line, go up.
Okay.
Go up. No, go up. Yeah, that one, yeah.
Okay.
Okay. Do you know the reason? Before you open it, you need to use image software to open your the projection, the CT slices.
Yes.
CT slices typically have three format. One is a fixed point format. Another one is a floating point format in refraction coefficient.
Yes.
Another one is a floating point format in attenuation coefficient. So when you import in the data, you have to open that first. When you open this data, you find the value are very small, like typically 10 to minus 7 or something. And this indicate it is refraction coefficient. When you're importing, regardless of what data format you have to convert into linear absorption coefficient.
Yes.
All right.
Yeah.
And okay, you don't just randomly checking the like apply scale factor cross images. You need to know what does that mean, why you check it.
Okay. Yes.
Like the lower, no, the lower one.
Okay.
Why you check that? You need to understand what does it mean. Can you get that import dialog again?
1 second. Actually, I import the data and
Okay.
yeah, it's importing that. That's fine.
When you just get the import and the dialog. So earlier, like you check crossing images, crop images. Do you understand what the crop images mean and what's the purpose for it?
No.
Okay. The general rule of thumb is that if you don't understand, don't do it.
Okay.
You do anything, you need to understand.
Yes.
Okay. And there's each of them has a purpose. And in general, is if you don't understand, don't do it. If you don't know option, don't check it.
Yeah.
That's the general rule of thumb. But it's same as you use any software.
Yes.
If you checking different options, you don't know what the option mean, and can only mess it up.
Yeah.
That's do you understand? That's
Yes.
a general rule. I guess Sam will be familiar with all sorts of different software, right? You run a different softwares, right? You use
Yes.
softwares. So in general principle is for the software option. If you don't understand it, don't use it.
Yeah.
And you check options, you can only mess it up. Like cross images, crop images. If you don't understand, uncheck it.
Okay.
Yeah, you're unchecking it now because apparently you don't understand it. Right?
Actually,
So
I was trying to practice this, and I'm also reading your article as well, and
yep.
just try to practice so that I know
When you
how it works.
practice and
Yeah.
you try the different options to understand it and see what's the effect.
Yeah, because it's not coming. That's why I was unable to do anything.
Okay.
Yeah, if it shows something, then I can check if I change something, then what happened. Yeah.
Yeah, need to understand. If you
Yes.
check that option with a
Yes.
different value, what
Yeah.
does it what it does? But this is a very, very simple to understand. Basically, cropping image, like any software, like image J or whatever the image, there's all have this cropping image function.
Yes.
Do you understand?
Yes.
Okay, maybe I'll challenge Simon to explain what's a image cropping. This is a means.
I think what I get, for example, we have one image like this. So when you set the offset, for example,
Yeah.
now you set 0, that means you have the full image. But if you set the offset, for example, 1, so if you take so this is the x and this is y. So if you set the offset, that means you only take maybe the from here. So this is the offset on the y direction, and this is the offset for the x direction. you not cut the image from the old boy here, but you move the old boy to somewhere here.
Okay. All right. Does anyone have further questions? And I think that Simon did a very good job explaining it. If you're cropping 0 then 0, that means
Yes.
you're not doing anything.
Yes.
Yeah.
All right.
So I'm
Okay.
just signing into a workspace, a Siro workspace, and I can show you where that cropping is useful, where you might want to use it. So it'll take a little bit, but once it's up, I'll let you know.
Okay. I believe Simon, when you play with the sandstone data, you tried the cropping, right? Did the cropping? I saw your shape looks different. Have you? Okay. Anyone else did anything? Or any question? Shima, have you tried yours case?
No, I actually didn't have access to my Windows laptop anymore, and I couldn't install. Like I have a Mac now, I couldn't install this DCM Lite on it, and I requested to install DCM Lite on my RMIT desktop, but they haven't done it yet. So
Okay.
unfortunately, I
all right.
didn't have access to the.
So you
Yeah.
don't have the admin access to the machine.
No.
Okay.
Everything takes too long with IT. Like whatever request that you lodge, it takes a few days at least.
Yeah. So your case, that's also a very interesting case. So just looking the interface or the gap between the two aluminum. So I encourage if you can.
Yeah, I actually do not have the CT data of that sample yet either. I don't have access to the Bandura lab right now due to quarantine and everything. But yeah, I should ask the PhD student to probably get a CT data from that for me if I want to work with it.
But first, you need to tell the student what's your sample look like.
Yeah.
You need to work that out.
Yeah.
Yeah. So this is like Sana did at the chicken egg. You first need to work out what is your sample look like.
Yeah.
Before the CT lab can do anything. If you just walk into the CT lab, you want to get anything.
Yeah,
you need
sure.
to get your sample prepared.
I can share and show you what the trimming is for now. I'll just quickly share my page. Okay, so say this is my image, and I want just to model a certain area of it. So I don't want to model this whole entire thing. So if you remember down here, you've got your I and your J. So say that was the point that I wanted to model from, and I wanted to model, say, all of it from here to there. That would be my offset. So X offset would be 286, Y offset would be 448. The sample grid that you set up then dictates how much more of the sample you're going to get. So you only need to make one offset of where you want to start the importing of the image. So say up here, and then the X length that you put in is the sample grid, and the Y length, and then the Z length is the how many of these images. So that's essentially where the X offset is. So you literally, when you're doing your import, you just mark down these numbers and put that in your X and Y offset.
Okay.
So pretty straightforward.
Yeah. Can I have a question here?
Yep.
So I work with with our 6061.
Right.
So wait on here, I check the density is 2.7.
Yep.
2. I enter it here and I calculate the X-ray. So when
Okay. So first, go back one step. How you work out the formula?
I have not.
How you enter the you need to enter a formula for it.
Yeah. Composition.
What is it?
Composition.
Aluminium 60.
Yeah.
What is it?
I just enter like it.
Now that's not the way. This is a molar formula.
Okay.
No,
So,
it's not even. It's a molar formula. This is what you put in there is just a.
Okay. This is a commercial name.
Yeah.
And the molar formula is the relative ratio of the elements.
Yeah.
So in this one, you said, okay, it's aluminium 6061 aluminium at the atoms. Actually, Al6061 is alloy. All right.
Yeah, it's got magnesium, silicon. It's got a bunch of stuff in it.
So go back. You need to search for aluminium 6061 and find. Okay, this give you the elemental by weight. Right.
So in case like, for example, the percent by mass, we will have a range like it from 95.
Yeah, just take a middle number.
Okay, yeah.
As an approximation. Just just pick the medium or the average. Just for argument's sake, say aluminium is 97. Magnesium is 1.
Yeah.
Okay, and silicon, etc. You get a smaller number.
0.6.
Right. Make sure they add to 100.
Yeah.
Then from this weight ratio to change to a molar ratio.
Yeah.
Okay.
Yeah.
So the first of all, your formula is not correct. So the absorption curve and all that is not correct.
Okay. Yeah, because I think I saw the curve look like it. So
they'll be all like this shape, but the actual value will not be correct because you didn't correct the molar formula.
Yeah, so for example, if the curve look like this, so when I take the X-ray image, so the beam energy, I can select it, for example, 30. That
okay.
Okay, right?
No, there is one phase, single phase material. This is a single phase material.
Yeah.
Then it doesn't matter. The energy is because you are not trying to resolve multiple materials.
Okay. So for example, like in this paper, you with I think only
yeah, okay.
Titanium.
Yep.
So for example, like here titanium 3.5 or 4.5, and then I think we have quite the same curve, right?
Yeah, the same shape. They all have this very similar shape.
So in this case, for aluminum 6061, I have to like is that okay if I just put it like this, like the name like it, and I search on Google and the density is 2.7, and then can enter it here, and then
no, it doesn't work. The composition is a molar formula.
Okay, so you mean the cap, like I have to enter, like for example, for this one, it will have aluminum, magnesium,
Yeah.
and zinc. Right?
But that's weight percent. So you need to convert
This is
that
weight
into
percent. You
molar.
need to convert it into a molar percent. And for a single phase of material, it's very easy. You just get the weight percent divided by the elemental weight of each element.
Yeah.
Okay.
So it will be something like it, right? So the mass weight is 1 and CNIT is 0.6 or something like that.
Oh, this is okay. So this is a weight, formula, weight percent formula. You need to change that to a molar weight, a molar percent formula.
So, for example, like so that from the Titan 64, he has the mass in Titan 8 or 6.
Yeah, yeah,
yeah. That's a different formula. Yeah.
yeah.
Or is that Z formula and Z formula is the same, right?
No.
Oh.
You say the TI64, if this is a weight percent formula, is a TI90 AL6V4.
Oh,
Then you TI64 is a commercial name. People call them that's a commercial name. The weight formula is TI90 AL6V4.
Yes.
Yeah.
okay, so
This is a
a
weight
weight
formula.
formula.
Yeah.
And
The
the other
other
one's
one is a molar formula. Yeah, this is a molar formula.
You see,
So
obviously, aluminium's
I
very light, so it makes a lot more of the sample.
Yeah. So that's got a weight formula. To convert that is from a weight formula to a molar formula is if you divide like you just use an TI64 as example, and you divide 90 by the atomic weight of titanium. That's I think 47 or something. And then you divide 6 by the molecular weight of aluminium.
Okay. Yeah.
And then normalize it. You'll get to it.
Yeah, and then divide it by the normalized values, and that'll get you your molecular formula.
For a single phase material, that's a simple way to do it. But you cannot use a commercial name, and you cannot use weight formula.
I might put together some examples for next time, Sam. I'll put together two or three examples of converting weight to molecular.
Yeah.
And we'll go through them next time.
I thought this would be fairly simple. If you understand what is a molar formula, it should be fairly simple to do.
I think once we go through an example, it'll seem very easy. It'll clear everything up. I think it won't be too difficult.
I thought that I'll try to get Santa to work on that case. So once you work through a case, you understand it.
Yeah.
And I'll try to encourage whoever is not understanding, try to need to do a case. Shima, do you your case is too simple, just a single element.
It's also an alloy of
Alloy.
aluminium.
What alloy is it?
So it's aluminium. 5754.
74. Okay, so they're similar. So if you look at it, just so
Yeah, I think I should go the same way that Simon is going.
yeah, exactly. Just they are all two different commercial names. Just they'll still have this very much the same list of elements, but a different percentage.
Yeah.
So your case and Simon's case will be very, very similar. You just have different numbers for different elements.
So
Yeah, so the-
I only need to care about the approximate.
okay.
So in here I only to care about the aluminum, magnesium, and zinc, right? All the other
Yeah, you
percentage
need to get
are
all
too
of them.
small.
No,
Okay.
you have to. Okay, even say for instance here, like iron, and yes, particularly like copper, they are very
Yeah.
small percentage.
Yeah.
But copper is a very high X-ray attenuation. So even if a small percent, it will if you compare silicon and copper, and silicon will have a much smaller effect than the copper, even if silicon has a smaller percentage, a larger percentage.
Yeah.
Okay, even a magnesium. If you just compare, magnesium is about 1%, copper is 0.3%, right?
Yeah. 0.3%.
Yeah, but
So
copper will have a higher effect.
you definitely have to, make sure you're very careful to include, especially the highest attenuating phase. So my recent work, the coatings are mainly made up of ZRB2 and ZRO2. However, I was leaving out 3% of HFB2. I was just leaving that out of the current calculation. The difference of when I put that 3% back in was the difference of getting incorrect results and getting pretty much exact results. So literally just by leaving out the 3%, I was getting much lower values than I should have gotten. So yeah, it's very important to especially know which, and it's basically which element is the biggest one, which has the most protons, basically.
So so the heavier, in general, is that the heavier element has more role. Okay.
I have more questions. So like after we can calculate the molecular formula is that when I enter it to a DCM software, so I enter it like titan and it will be for example aluminum, right? And then bone.
You have to add a density in there as well. Remember?
Yeah.
Also
You
figure
figure out your density rule of mixture.
Yeah. So I have to add some number here. But is that for example, if I work with the titanium 64, I calculate it, and when I have to enter
not this way.
No.
TI64 is just one phase. They are not separate. Okay.
So that means like I just need to enter like
1.
in here will be something.
That's right.
Okay.
Then the density, you need to give a density.
And then I can form density.
Yep.
Yeah. Okay.
Then this will give you the right answer for TI64. This will be the correct absorption curve for TI64.
So what wrong if I because when I enter this one, even if I enter it like titanium 64, D64 is still okay.
All right.
What wrong if I enter it?
That name is just that's a coincidence.
Yeah.
Because that still look like the molecular formula can also be written that way. So the syntax looks right. But you say you say the there are other alloys called such as Inconel. That's also another commercial name. If you put that on, you would say incorrect.
Yeah. So
But
that is that the name, right? I can put any name I want, or I have to go to
yeah, you
or
can
make
rename it.
from
Yeah, you can rename it. There's no effect, but the formula must be right.
So, but
Normally,
when I put the name here, and then because the density I search on Google, so where the molecular formula is.
sorry.
You won't see. Are you saying where can you? You won't,
Oh, all right. No,
not many people will put out the molecular formula. It's a lot of people don't need to do this, so they will
Yeah.
consistently refer to it as titanium 64. I was looking for this myself and hoping that someone else would have done it, but they hadn't, so I had to do it myself.
the first of all, you can have a different name, but the formula and the density cannot change.
Yeah.
You can have a different name. You click that rename channel.
Yes.
Left. No. Left. No. You do the okay. Still check it.
Oh, yeah.
You can give it a different name.
Yeah, like I just
Arbitrary,
call
you
it
can say TR64, whatever you said.
Yeah.
So that channel name will change, but you cannot change the formula and cannot change density.
Oh, okay. So the name here could be changed, but the formula should be.
Formula cannot be changed. Yeah, the default way to get is just the formula get the channel name.
Okay.
That's a convenience. Convenient.
Okay.
You can
So
the name can be anything. You can say TI64 Lab 22.
Yeah.
You can say anything, just a name.
Okay.
You understand what?
Yes. Yeah, so because when I rename it, so it automatically changed the name here. So I also did name and did name are similar, but it's not similar.
No. The name and the formula, the default is the same, but it doesn't necessarily to be the same.
Okay. Yeah.
Understand? Is it anyone clear about
Yes.
SOBI?
Yeah.
Okay. Yeah.
Okay. Just the default name is a formula.
Yeah.
So titanium in a one phase alloy. So in my case the same, right? For the aluminum 6061, is that also
Is a one phase, yeah. So you channel name you can call the aluminum 6061.
Yeah.
But the formula is different.
Okay.
You have to work that out.
Yes.
Okay. And if it's for Shima, there's aluminum is 6074, right?
It was 5754.
5074.
Yeah.
Six or five?
5.
Oh, 5. Okay, right.
5754.
5 and 5 4. All right. Okay.
Yeah,
So that's a
that
different one. That's a different one. But there'll be the like if you just look at the list, that's still the same, but just a different proportion.
Yeah.
Yeah, the density is a bit different. Yeah. Okay. Can I do this and I'll try if we're going to continue the next time. The get assignment to work on your case for the formula. This will be a very simple for your case. It'll be very simple because a single phase material. And the assignment need to work a little bit more because of two phase material.
Yeah.
But I need to understand that's a molar formula.
So for the two-phase material, we will add two formulas in the DCM.
No, one formula.
One formula. Okay.
Because when you okay, all right, no, okay. Two point here. When you estimate the sample size, you use one formula.
Okay.
Because that's one sample.
One sample. Yes.
They're mixed. when you do the DCM channels, you need to have a tool because you want to separate them.
Yes. Okay.
So you need a two separate formula and a combined formula.
I got to jump off, Sam. I got another meeting
Yep.
at 3. We're trying to sort out getting in.
Yep. Yeah, we need to finish. We need
during
to finish
lockdown.
anyway.
I've got to
Yep.
go.
Yep.
See you, everyone.
Okay, thank
Thank
you.
you.
Thank you.
Thank you. Bye.
Okay.
Thank you.
So we also need to finish anyway. So
So we are going to have 3 composition channels.
sorry.
So we're going to have 3 composition channels.
In the calculation, you only need 2.
Okay. Yes.
One of them is just for when you estimate the sample size, you need 1.
Okay. Yes.
Okay. So need to work this out. And I thought this would be a simple concept. It surprised me. It'll take a bit of time. But good, we need to clarify, get this all clear.
And thanks to you. You are clearing
Yeah.
everything. Yeah.
And Simon, it's the access the imaging will be further down the track. So you may not need to worry too much to get the sample, but you need to understand what kind of a sample can be imaged.
Yeah.
I think at this stage, but for Shima, you want to get your samples specified at least. Tell the student that.
So, for example, in my case, in my object view, for example, like have this shape, and I want to check the porosity. So, and I feel interested in the intersection part here. So
Yeah.
should I cut like cut a bit up here, like
Yep.
at the cylinder shape,
Yep.
and then do the same experiment like that, like maybe cut it to be a cylinder, and then set up the X-ray. Oh, I have one question about here about the pixel size. So, like, do you have any recommendation for choosing the pixel size when?
All right.
Yep.
Yes. Right.
Pixel size is when you work out the sample size and divide by 1,000.
Yeah.
That is typically the pixel size.
Sample size divided to 1,000.
By 1,000. It could be 2,000, but just use 1,000 as a guide. If it's a sample size is a millimeter, pixel size will be 1 micron.
Is that why you select here? So the it is the physical size. And,
Okay.
the pixel size here is 6.5
Okay, all right. Okay.
micron.
This is the all right. This is all right. In synchrotron imaging is a parallel beam.
Yeah.
And the detector has a pixel size.
Yeah.
Right? If you're in a parallel beam, if you put a sample, and what the pixel size will be the same as a detector pixel size, right?
Okay. Because here we're
That
using the
anyone-
10 optical lens, right? So the actual
Right.
pixel size will be 0.65 micron.
Yeah, so you get an effective pixel size. At the sample point, you see the pixel size at 0.65 because it has a 10-time optics. But in the lab CT, this is different. They use a geometric magnification. So you're adjusting detector sample and the source relative distance, right? And you have a different way to estimate the effective size.
So here is no, each voxel have a physical size.
Right.
Okay, yeah.
Okay. For the sample point, you say 0.65 as the pixel size.
I feel a bit confused here, like from this one and
Okay.
this
Let's
one.
talk
How
about
do
the
you
sample language.
get it? Because 0.65 multiplied by 580.
580. That should be the first. That is the length of the sample region.
So like 580 multiplied by 0.5. 377. Why do you have 159 here?
Oh. Okay. There's a mistake.
Yeah, because X voxel here the
Yeah,
sign
yeah,
of X
yeah.
voxel and yeah.
Now, this is incorrect. So if you review this paper, you'll get rejected. This is obvious. Yeah, this is obvious error.
Okay.
Yeah. I think yes. If you look at this is. I think this is only a subset of that sample.
Yeah, because it said the reason
This is not correct. Yeah.
correspond to. So I think it should be like 377.
Yeah. That's the incorrectly calculated.
Yeah, because I got a bit confused when I calculate that. So
Yeah, right. Yeah. Fortunately, you are not the reviewer of this paper. Otherwise, this would not get published.
It was published so fast that time, you were saying.
Yeah, this
Yeah.
paper, the reviewers has a very friendly reviewer, but
Yeah.
you see, this is when the student did it, maybe tried the different sizes and updated one and it didn't update the other. You know what I mean?
Yeah.
Try the smaller region and to find out, okay, even larger region looks fine. Just change the region pixel size, but it didn't update the physical size. Yeah. Yes, your understanding is correct. So that number is incorrect.
Okay.
Okay. Yeah, it's good. But yeah, it's really good. Simon is really good to look at that point. That's really excellent.
Hi, Sana. I think you sent me an email asking about the bound.
Yeah.
Haida.
Yes. I was asked, then I asked the Sam about that, the trimming of the. You have used another software for that?
Oh no.
You said something boundary.
Yeah. So the boundary here, when you select here boundary, you just go here, to view. You have to select the grid first. And then here you just go to view boundary and then cylinder and select, for example, 100.
Okay. Yeah, I got it.
Yeah.
Thank
So
you.
you have something like that, yeah. So when you show the result, let's select here boundary and
I can't see your screen.
You did have to share. Oh, you intended to share your screen, are you?
yeah. Yes. So yeah, as I said, now is that go to here, and you can set the
Okay. Yeah, got it.
boundary,
Okay.
and then after, yeah. And for all the other users, select to show the boundary only.
Yeah. If you
Yes.
select the boundary, then it's all the display and the calculation is all in the boundary.
Also, like for example, if we in the calculation of the property here, if I select the boundary here, it only to show, but in case when I select to calculate here, if I select the boundary here, if that affect to the result, to the calculation, is that a
yes,
save time?
yes.
Because
If you
the boundary
specify the boundary, and the relevant calculation will be just within the boundary. It will ignore anything outside.
and that may be run faster.
Slightly, not significant.
Okay.
Because you still need to go through all the points.
Yeah.
And if it is found as a outside the boundary, just skip some part of the calculation. You don't want to make it significantly faster, slightly.
Yeah.
One more thing. In your article, you have said that boundary, we can select the sample based boundary. Yeah.
Sorry, what's it?
If for in your article, you have in for the DCM, you have
Yeah.
said we can select the sample based boundary.
Yeah.
But it's not coming in my DCM. What do you think is what happened?
Okay. There's a revision that happened, so it may not exactly the same because
Okay.
that's an earlier version.
Okay, yeah, because it's in your article it was like you can select the sample based, but it's not
So
coming
you
now.
can select the sample. All right. Generally, that's I want to recommend that because it's a very slow process.
Okay.
Um,
So which one you
So,
you recommend
the
we should
channel
choose?
value based channel. Yes, the channel value based. That's what the sample based called earlier.
Okay, okay,
But this is a very slow,
okay,
and they just using the default the channel cluster based. That's much faster. Or as Simon did, they just use a geometry like a cylinder, cube, or whatever.
okay.
So the Simon you select use a cylinder as a boundary.
Yeah.
So you can do it that way.
Okay.
Okay. Any other questions, or if not, then we decide, do we want to continue this pattern or not?
Yeah.
Who want to continue? If the majority want to continue, we'll continue. Otherwise, we do another one in 2 weeks time?
Yes, it would be very good.
Okay, so Sana, yes. Whoever, another yes? No? Okay. Shima, you got a yes? Is that a yes?
Yes.
Okay. How you do that? Okay, so
There are reactions at the bottom,
okay,
like next to share.
all right. So if it's just a feel it's a waste of time, and then we'll do it different way. And any other suggestion of other format? Is that a format all right or not?
Good.
Format.
Like you wanted to do different way. I thought if you try to get everyone to run up your program, and that has for relevance. So we continue in the same pattern, same
Yeah.
way, right? All right.
Yeah.
Next, 2 p.m.
Yep.
I can
After
check
2 p.m.
my calendar. Here is all clear. Then
Shima, your COC is coming now in October.
sorry.
Shima, COC, your COC is coming now in October. You're doing
CO.
PhD?
No, I'm a postdoc research
Okay.
assistant. Yeah.
Okay.
I did the whole PhD thing. I thankfully
Oh,
finished it that.
Mhm.
okay. You did it from the RMIT?
No, I was from UniMath. I even was from like computer science, so I changed a lot of things. Discipline in university.
In 2 weeks, that'll become 2nd of September, right?
Yes.
Oh, 2nd September. Oh, 2nd September.
2nd of
Wow.
September is the last
I'm
day
in
of
a
lockdown.
Take it a slow
conference.
week. Yeah.
I'm in a conference next 2nd
or
September.
maybe 3 weeks. Yeah.
Yeah, 3
3
weeks is okay.
weeks.
Because
3
in
weeks.
September I have my vaccination as well.
Yeah, 3 weeks. That'll work. So then we do 9th of September. That all good?
Yes.
Yeah.
Okay. All right. Yeah. So it's good. Don't worry about it if you make a mistake or anything. Try to work something out, and then the correction of your own mistake is also other people learn from it. So we'll try that way. Okay. And Emma has been quiet. So we'll also get get hopefully by next 3 weeks time. Sherry will be back, so try to organize a training and for the new facility.
Perfect. Then I
So,
can actually start doing this stuff myself.
yeah, and also the sample. We need to also get the sample. Have you maybe you work with Darren
I
to get the
I think
sample?
Darren had printed a couple. He
We
showed me a
need to,
couple that he'd printed. I'm not sure if he was planning to do any more or not.
well, we need to get a workshop to get the sample
Yep.
prepared. We need to do the corrosion test.
Yeah, so I think Darren's already made them. He just needs to get them machined down or whatnot.
Yeah, just need to get a push in the workshop. So we need to get that moving. So we'll get there gradually. So I can see that that's and then I need to also get to the sample
Yes.
and need to do the CT lab training.
Yeah.
So Shima, you don't want to go to the CT lab training, are you? No.
For the CT lab only, or no, I don't think we need that.
For the data.
Yeah.
I think that you need to get your sample designed, so you know what sample you run. And I still, even if you don't run experiment, best you still do the training. You know what is going to happen in the lab and what are the potential
It's just
potential
1 hour
parameters and
training.
things you need to note. That'd be useful. The don't worry if the city people says, "Oh, you won't be able to resolve it." And for your case, if you use an image segmentation, it is challenging or may not be able to resolve it. But
Um,
DCM is just imagine DCM will all have a factor 10 better resolve it. Even if it's you get at the case and the CT people says no, you can't resolve it. Don't worry about it. We'll get something out. Can, and for Simon, it's really just prepare for the next step. And also Simon and Sana, you have this is working on the same case, so both are cold spray.
Yeah.
Encourage you to try to communicate closely.
So you already sent me the link for the Cyro induction, please?
Have you received or not? We'll talk about later.
Yeah, no problem. Okay.
I'll find out. You need to get that organized.
Okay. Thank you.
And I said, come and the Emma and Simon will help you.
Yeah.
All right.
Okay.
Is there anything else we want to talk today, or we can close it today?
all good.
All right. Oh, good. All right. Thank you.
Good. Thanks, Sam.
Thank you. Yeah. Thank
Take
you.
care.
Thank you. Bye.
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 Stop recording.